Okay, in this fourth part of the lecture, we now turn to the third and final objective of statistical inference, and that is interval estimation. An interval estimation actually follows logically from what we've learned about parameter estimation or point estimation and what we've learned about hypothesis testing. Actually, we're going to bring these concepts together. So what we've discussed so far, we've said that we can evaluate uncertainty in estimation by considering the sampling distribution of an estimator, and we then use that sampling distribution in the case of forming test statistics. Alternatively, we can kind of invert things and say we want to have a predetermine a level of uncertainty we're willing to accept and construct an interval estimator that's guaranteed to contain the true parameter value with a given level of uncertainty. And that's the principle underpinning interval estimation. And I'm going to just introduce some formal definitions, but really what I want to get to is confidence intervals, and I want to show you how they're calculated. So we'll do that again in a practical way. Let's just define the concept. So x1 to xn is a random sample. It's distributed according to this distribution depending on parameter theta. And an interval estimator for theta is the random interval specified by these two statistics, GL, the lower statistic on x, and the upper statistic on x, and this statistic, the lower one, must be less than or equal to the upper one, for all possible values of x in the test statistic, and this interval is intended to contain the true parameter theta. Now, associated with the interval estimator, we can talk about a coverage probability, and the coverage probability is simply the probability that parameter theta lies within that random interval. So that's what we're interested in, constructing a random interval and the probability that theta lies within that interval. Now, interval estimators, along with measures of confidence, are most commonly used to construct confidence intervals, and that's where most of you will come across this concept. So just two more things we need to define before we can go on to look at this. First, a confidence coefficient. For an interval estimator of parameter theta, the confidence coefficient is the infimum of the coverage probabilities. That is, it's the greatest lower bound of this set. And so an confidence interval, if an interval estimator is designed with confidence coefficient 1 minus alpha, and we're going to set the value of alpha, then we're interested in the probability that theta lies within this interval being greater than or equal to 1 minus alpha. That's the level of uncertainty that we're going to set by choosing alpha. We refer to that interval in this context as a 100 times 1 minus alpha % confidence interval. So what does this mean intuitively? Well, confidence intervals are probability statements about the random interval in which we think a parameter lies, given the sampling distribution that we observe, with a predetermined probability. Could be 95%, could be 99%. And so, in that sense, we can think of confidence intervals in two very closely related ways. First, a 100 1 minus alpha % confidence interval, and let's say we set alpha equal to 0.05, then an 85% confidence interval for theta gives an interval over which we can be 95% confident that the true value of theta falls if the model is correctly specified. Secondly, the confidence interval we can also think of as giving us the set of hypotheses, the interval of hypothesis, or possible values of the parameters that are compatible with the estimates that we have. So, in that sense, when we go to form a confidence interval, all we're going to do is invert a test statistic, and it's really as simple as that. That's all we need. So let's just look at how this works. We have an estimate of theta, and as we know, we can calculate z statistics, which are going to test hypothesis about theta. And we're going to use z statistics, invert them to form the confidence intervals as follows. Now, from the definition of a test statistic, any value theta naught is incompatible with our estimate if the value of the z statistic is greater than the critical value or less than the critical value in the case of a two-sided test. So as long as this is true, and this is true, then theta naught is incompatible with our estimate. That is, we can take this with a bit of algebra incompatibility, take this over to this side in both cases, solve this expression for theta naught, and that is what incompatibility implies in terms of our test statistics. We can write it in this form here. So if we turn the greater than into a less than equal and the less than into a greater than equal, that must be that compatibility, in other words, all the values of theta naught that are compatible with our estimates can be written in that expression there. So if we write it in this way, bring these two parts together, then the set of all theta naught that satisfy this double inequality is the 100 1 minus alpha % confidence interval given by this expression here. Theta minus sigma over root n times the test statistic, theta hat plus sigma divided by root n times the test statistic. And it's as simple as that. That is how we form confidence intervals. So let's do it in an example. Let x1 to xn be independent and identically distributed according to a normal distribution with mean mu and variance sigma squared. We estimate mu using the sample mean, x bar. In a one sample z test that we looked at earlier, we saw that this quantity here is normally distributed according to the standard normal distribution. So let's say that our estimated value of our estimate is 0.050, and we know in this case, because it's a z test, so we know sigma. We know that sigma over root n equals 0.005. At the 5% level, the critical value of z is 1.965. Then the corresponding 95% confidence interval for mu based on the sample mean, we just calculate using this expression here. That is our estimate minus 0.05 times this quantity here, times the critical value of z, being less than or equal to beta, less than or equal to 0.05 plus 0.05 times the critical value of beta. And this gives us our confidence interval, calculated as simple as that. And that says that we can reject hypothetical values above 0.60 and below 0.40. Any hypothesis within these limits is not rejected given our estimates. So it's telling us the set of hypothetical values that are consistent with the estimate we've obtained given the sampling distribution that we've observed at the 5% critical level of z being 1.965.